Hello, everyone. This video is the last video for my Camden County College students. I will be covering section 7.4 of your textbook, which is about hypothesis tests for population proportion. So this is it for today, and so let's get started. All right, so let's get right to the textbook. All right, so in 7.4, we're going to be talking about hypothesis testing for proportions. We're still going to be using the 6 steps that I taught you before, including the use of p-values, the calculation of p-values, and comparing them to alpha, which is a level of significance. We're going to be using that decision rule. We're not going to be talking about rejection regions or anything like that. It does describe it in this section a little bit. So again, you can review that on your own in case you run into a homework problem. But as far as test number 3 is concerned, I will not be testing you on rejection regions. So just follow the steps that I'm showing you in today, and the same steps that I showed you before on 7.3 and 7.2. The only difference is that the formulas for the test statistics are a little bit different. All right, so what we're going to be doing today is, now one thing I have to clarify, I think on my sheets here, I think I made just a slight little error. I don't even know if it's an error, but in another textbook that I'm using, when we talk about determining if a hypothesis test can be used, we test to see if the sampling distribution is normal. And notice in this book here, they use NP is greater than or equal to 5, and NQ is greater than or equal to 5. And in my notes, I use 10. There's other textbooks that say 10. I'll make the change in my notes for you to show that it's supposed to be 5 instead of 10. But it doesn't really matter, because in pretty much every case that I'm going to show you, NP and NQ, which is the same as n times 1 minus b, it's way above 5 or even 10. So it doesn't really matter. In both cases, the sampling distribution is going to be normal. All right. So every case, pretty much every case I'm going to show you, you don't need to worry about that. But just know that in this textbook, they use 5 here. And I think in my problem solving, I use 10 because I'm used to seeing that in other textbooks. So don't worry about that. It's going to be well above 5 or 10 when we multiply n times b and n times q. But I'll show you that in a minute. Now, the big change in this section is that when we're looking at hypothesis tests for proportions, we're going to be using this formula here. Now, the numerator of the z statistic, and we always use z statistic for proportion, hypothesis test for proportions. We never use a t. The t was only used in section 7.3 when we were looking at hypothesis tests for means when the population standard deviation is unknown. For proportions, we always use a z. The numerator is p hat, which is our sample proportion, minus p, which is our hypothesized population proportion. And then we, in the denominator, we have our standard error. It's the square root of p times q. Now, q is 1 minus p. Just know that I use 1 minus p, and the book sometimes uses q, divided by n, which is the sample size. Notice that we do not use p hat and q hat in the inside the square root. So for hypothesis tests, we always put in the square root the hypothesized value of p, not the sample proportion. All right. This is different than for confidence intervals. If you remember for chapter 6, when we talked about confidence intervals, we use the standard error, the square root, when we used it in the margin of error formula, we used p hat inside the square root. That's because we were estimating P. We didn't have any idea what P was. Here, with a hypothesis test, we are hypothesizing what P is. And therefore, we're going to put that hypothesized value, whatever this number is here, we're going to put it inside the square root. All right? So we'll go through the 6 steps. Let's just look at an example here, and we'll try to do it. Do a couple of examples before I show you the problems I did at the back of the book. All right, it says hypothesis test for proportion. A researcher claims that less than 45% of US adults use passwords that are less secure because complicated ones are too hard to remember. All right, well, the first thing you can see is this is a claim and it has less than in it. Less than is something that we use in the alternative hypothesis. So as you can see down here, when we state our null and alternative hypothesis, the claim is the alternative hypothesis because less than is the same as this symbol here, less than. That means the null hypothesis has to be the complement of it, which is P is greater than or equal to 0.45, and there's the equal to signs in the null hypothesis. All right. In a random sample of 100 adults, that means N is equal to 100. 41% say they use passwords that are less secure because complicated ones are too hard to remember. So 0.41 is going to be our sample proportion, okay, P hat. All right, anyway, it says that alpha is equal to 0.01. That's our level of significance, 1%. Is there enough evidence to support the researcher's claim? So once again, the researcher's claim happens to be in the alternative hypothesis. That's why we want to know if there's enough evidence to support this claim, which is the same thing as saying, is there enough evidence to reject the null hypothesis and support this claim? All right. Now they're going to use, in this case here, they're going to use critical values and rejection regions, and I don't want to do that. So I'm going to show you with your calculator how to come up with the answer using the p-value. All right. So just give me a second. I'm going to write down all the information that we need for this problem. I think we're good. So let's go to our calculator. What's nice about these problems is that you're never going to have a data set for this. They'll give you p hat. They'll give you the sample proportion. And the only thing that you need is the sample proportion and the sample size. And you can do this problem pretty easily. So the first thing that we want to do is calculate our test statistic. So once again, if we go back to the book, let's take a look at that test statistic again. Here it is. This is our Z formula right here. That's our test statistic. So we'll go back to our calculator. And again, remember, when we calculate test statistics, we always use parentheses in the numerator. We always use parentheses in the denominator. So I'm going to open up a set of parentheses. And the numerator formula says it's p hat minus p. P hat in this case is 0.41. All right, so it's going to be 0.41 minus the hypothesized value, which is 0.45, close parentheses, divided by, and then we'd have a square root in our denominator because the standard error is the square root. Now remember, inside here, we're going to use p, the hypothesized p, which in this case is 0.45. We're not using p hat. All right, so we're going to type in 0.45 times. Now, q, or 1 minus p, is just 1 minus 0.45. And you can actually put parentheses here and put 1 minus 0.45, but I happen to know that's 0.55. Divide by the sample size, which is 100. Right, and hit enter. And there is the sample, the test statistic, Z, negative 0.804. Now, if I'm doing this strictly with my calculator and I want to get my p-value, then I'm going to store this test statistic. And I'm going to hit store and then hit alpha. And I just use T, but you can use any letter that you want. And so I've stored this number, this test statistic, in T. Now, if we go back to the problem, Notice the alternative hypothesis has less than in it. Remember the rule. The rule says that the alternative hypothesis tells us whether we have a left tail test, a right tail test, or a two tail test. Less than means left tail test. If it was greater than in the alternative hypothesis, it would be a right tail test. And if it was not equal to in the alternative hypothesis, it would be a two tail test. So in this case, it's less than, so it's a left tail test. All right. So let's go back to, and I don't know if they drew the curve here. Well, here's a left tail, but they're doing this curve down here is the rejection region method. Again, we're going to do the p-value method instead. All right, so it's a left tail test. Let's get back to our calculator. And we know with a z, we're going to use normal CDF to find the p-value. All right, so we scroll down to normal CDF. Now, a left tail test means that the lower endpoint is going to be negative 1,000. The upper endpoint is going to be our test statistic. Now, again, I just forgot what it was. I think it was negative 0.803 or something like that, but I remember I stored it in T, so I'm just going to put T down here. All right, that's why it's a good idea to store your numbers so that you don't have to write them down and remember them. All right, and scroll down, hit enter. And there you go, that's our p-value. So our p-value, if we round it to 3 decimal places, will be 0.211. All right, so let's get back to the problem. 0.211 is our p-value. And what is alpha? Alpha is 0.01. So when the p-value 0.221 is greater than alpha is equal to 0.01, we know that that means do not reject the null hypothesis. So when the p-value is greater than alpha, we do not reject the null hypothesis, and it's clearly not in this case here. All right, and so what is going to be our conclusion? And actually, you could see the same conclusion if you use the rejection region method. There's not enough evidence at the 1% level of significance to support the claim that less than 45% of US adults use passwords that are less secure. Now, notice that here they say not enough evidence to support the claim. Why do they say that instead of not enough evidence to reject the null hypothesis? Well, once again, the claim is the alternative hypothesis. So when we reject the null hypothesis, in this case, we're supporting the claim. That's why it's being stated in that way. All right? So do not reject the null hypothesis because the p-value of 0.211 is greater than the alpha 0.01. The write-up down here, they're showing you how to do it using the rejection region method, which again, I will not test you on. All right? But you can look through it, and in case you run into a problem in your homework where they do ask you to find critical values and find the rejection region and all of that, then you have a write-up right here to show you how to do it. All right. So let's see. Now, try it yourself here. Let's look at this one. This looks like a right tail test because let's read through it. A researcher claims that more than 90% of US adults have access to a smartphone. So more than means greater than. We know that that is in the alternative hypothesis. So the alternative hypothesis in this case will be mu is greater than 0.90, which means the null hypothesis is that mu is less than or equal to 0.90. So the claim is, once again, the alternative hypothesis. It says in a random sample of 150 adults, so n is equal to 150, 87% say they have access to a smartphone, so p hat is equal to 0.87. At alpha is equal to 0.01, so that's our level of significance, is there enough evidence to support the researcher's claim? Let's go back to our calculator and do this one. I'll just clear this out. And once again, we're going to do the test statistic, which is p in the numerator is p hat minus p. So p hat in this case, again, let's look again at the problem. p hat is 0.87, and p is 0.9. Right? So 0.87 is p hat, right? And 0.9 is the hypothesized proportion. All right, so just verify that. 0.87 is the p hat, and the claim is 0.9. All right. Now, let's go back to the calculator. So we'll close our parentheses. Denominator, let's say divide by, and it gets its square root. Once again, we're going to use the hypothesized proportion inside the square root. So it's going to be 0.9 times, and then it's 1 minus 0.9, which is 0.1, divided by the sample size, which is 150. Hit enter. Negative 1.2247 is our test statistic for Z. Again, I'm going to store it. All right. Storing always a safe way of remembering these things. If you forget it, or if you needed to write it down, probably better to store it. So I'm going to store, and again, I'll store it in T. Remember, whenever you store a number, it replaces the number that was in there before, so you don't have to worry about that. Now, the alternative hypothesis is going to be greater than, because that's what it says the claim is, greater than. So that's alternative hypothesis. That's a right tail test. So I'm going to do, now, don't be fooled by the fact that the test statistic's negative in this case here. We always look at the alternative hypothesis to determine what type of test it is, and it's a right tail test. So the fact that it's a negative T, a negative Z, doesn't matter in this case here. All right, so we're going to scroll down to normal CDF. Since it's a right tail test, the lower limit will be the number, the test statistic, which is T. The upper limit, again, I'll make it 1,000. And then scroll down, hit enter. Huge p-value here. That's because the test statistics on the left side of 0 is negative. So because and this is a right tail test, so we're finding the probability to the right of this number. It's going to be a big p-value, 0.8897. So it's 0.89, I think we would say. So this is definitely do not reject the null hypothesis. When you have such a big p-value, you're not rejecting the null hypothesis for sure. So in this case, the answer is there's not enough evidence at the 1% level of significance to support the claim that more than 90% of U.S. adults have access to a smartphone. All right. And the fact that the sample had less than that definitely doesn't support it. So this is a clear indication that there's not enough evidence to support the alternative hypothesis. All right. Let's go to the next page and see if let's see if the next problem that they have here is a yeah, this is a two-tailed test, so let's do one of these, and then we'll do examples in the back of the book of each of these cases once again, so that you can see the steps. All right, so let's look at example 2 here. A researcher claims that 51% of U.S. adults believe incorrectly that antibiotics are effective against viruses. All right, this is kind of interesting since we're in a viral pandemic right now. So notice that the claim is 51%, that 51%. Right? The word that here doesn't say less than, doesn't say greater than, or less than or equal to or greater than equal to. It just says that 51%. Same thing as saying is 51%. That's the null hypothesis. The null hypothesis is the claim. Since it's equal to, that means the alternative hypothesis must be not equal to. Right? So the wording kind of tells you what type of hypothesis it is. This is the hypothesized value, 0.51. You can see it both in the null and the alternative. All right, we have a random sample of 2,202 adults. That's our sample size N. This is out of those 2,202, 1,161 say antibiotics are effective against viruses. Of course, they're saying it incorrectly. At alpha is equal to 0.10, is there not evidence to support the researcher's claim? Now, this is actually not really correct, the way we stated it here. Since the claim is the null hypothesis, all right, what we're really asking is there enough evidence to reject this claim? And we can't really say is there enough evidence to support the researcher's claim, because remember, in hypothesis tests, we're either going to reject the null hypothesis or we're not going to reject the null hypothesis. We're not really, if we don't have enough evidence, we never say because there's not enough evidence to reject it, we're supporting it. No, we're not really supporting it. We're just saying there's not enough evidence to reject it. So the wording here is kind of not so great. I wish they would have said reject the researcher's claim. Is there enough evidence to reject the researcher's claim? That would be the better question. Now, when we look at the hypothesized proportion 0.51, notice that when we multiply it by 2,202, we're getting 1,123. When we multiply 2,202 by Q, which is 1 minus P, which is 0.49, we get 1,079. Both of these are well above 5, well above 10. It doesn't matter whether you use 5 or 10 as your number. Both these NP and NQ are both well above what's required for the sampling distribution to be normal. So we're definitely going to state that they're normal. So you can use the Z-test. Now, here's the deal. We have to use the test, right? So that would be step number 3 in our. So we state our null and alternative hypothesis. That's step 1. We do our little NP and NQ calculation to see if we have a normal sampling distribution. That's step 2. Step 3 is to calculate our test statistic, but they don't give you p hat in this case here. What they give you is the sample size, and they give you the number of people who said that they believe antibiotics are effective against viruses. So either you believe it or you don't believe it. Okay. So X, we could call this X, the number of successes, or the number of people who are saying yes to this question, is 1161. But p hat is X divided by N. So the fact that they have 1161 here, do not be fooled. This is not a hypothesis test for a mean. We're not saying that mu is equal to 1161, or excuse me, X bar is equal to 1161. No, this is a proportion question. You tell by the 51% here. So this is a proportion question. You just need to divide 1161 by 2202, X divided by N, and you get your sample proportion. And this number is what you put in for p hat. So whenever you see this type of question where they give you the sample size and then they give you the count of the number of people who answer a question in a certain way, know that that's X, and we're going to take this number and divide it by the sample size, X divided by N, to get our sample proportion. And that's what we plug into the first number in the numerator for our test statistic. All right, so p hat is 0.527. P, our hypothesized proportion, is this 0.51. That's the value that we put in our hypothesis test. And then our denominator is going to be the square root of 0.51, the hypothesized value, times 1 minus 0.51, which is 0.49, divided by 2202. All right. 1.60 is going to be our test statistic. So if we go back to our calculator, and I'm going to write these numbers down here so I have them. And I'm actually going to show you how to do this with our calculator in pretty much a couple steps. So it's very easy to do. Now, once again, they use the rejection region method here. I'll show you the p-value method with your calculator. How to do this. All right. Now, this is a two-tailed test, by the way. If you look at the alternative hypothesis, it says not equal to. So we're going to use a two-tailed test in this case here. So let's get to it. All right. So we'll go back to our calculator. Clear this out. Now, the first thing I'm going to do is calculate our sample proportion with the calculator. So I'm going to put in the numerator 1161 and divide by our denominator of 2202. Hit enter. And that's p hat. Now remember, p hat is being used in the test statistic formula. So it has all these numbers in it. You could round at this point, but why bother? You can store this. So I'm going to store this actually in another letter, and I'm going to use it in the test statistic problem, all right? Our test statistic formula. So I'm going to store this number here, this sample proportion. I'm going to store it in A. And I see A is right above the math button here. Just hit enter. And so my sample proportion is now in the letter A. So now I'm going to calculate my test statistic, open up a set of parentheses, and it's going to be in the numerator p hat minus p, right? Let's go back to the formula once again. P hat minus p is in the numerator. Now p hat I stored in A, so I'm just going to type in A there. Just do alpha A minus, and I know that my hypothesized proportion is 0.51. Okay, close parentheses, divide by square root. Now, what am I going to put inside here? The hypothesized proportion, 0.51. Don't put A in here, put 0.51 in here. And I'm going to multiply that by 1 minus 0.51, which I happen to know is 0.49. And I'm going to divide this by the sample size, which is 2202. So I hit enter. And there's my test statistic. Now, what am I going to do with this? I'll store it in T. All right. So you can see I stored my, I calculated my sample proportion and stored it in A. I used it in the formula for the test statistic, and now I'm going to store the test statistic number in T. So I'm going to hit the store button and store it in T. And now I'm going to, now you can see that the test statistic is positive. Even though this is a two-tailed test, since the test statistic is positive, I'm going to treat this as if I'm doing a right-tailed test, because it's to the right of 0. All right. So I'm going to go to my normal CDF. And because I'm treating it like a right-tailed test, my lower limit will be T. Notice I have it already set up like this, which is nice. This is why I like storing numbers. That way, if since the calculator kept what I did before, and I'm going to do this once again, something like a right-tailed test, I might as well use it. I don't even need to enter anything here. Hit enter. Now, this number here is the area to the right of the test statistic, 1.619. Now, because this is a two-tailed test, this is 1/2 the p-value. It's not the full p-value. So what do I do now? I'm going to hit my multiplication key, which means I'm going to multiply this number here, the 1/2 the p-value, by 2, and then this will give me the full p-value, 0.1054. So that is the p-value for a two-tailed test. I did have to multiply that area by 2, and this is my p-value, 0.1054. Go back to the problem. What is alpha in this case? 0.10. What is the p-value? 0.1054. This number, the p-value, is bigger than alpha. Okay? Bigger than 0.10. So whenever the p-value is bigger than alpha, we do not reject the null hypothesis. Now, I want to bring up something very important here. If I forgot that this was a two-tailed test and I kept the 0.0527 as my p-value, I would have come to a completely different decision, rejecting the null, because this is less than 0.10. But because I did remember, yes, I did remember to multiply by 2 because it's a two-tailed test, I get a p-value that's now larger than alpha, and therefore the correct decision is not to reject the null hypothesis. All right, and if you read through this right up here, and they did the rejection region method, notice that they came to the same conclusion. There's not enough evidence at the 10% level of significance to reject the claim of 51% of the U.S. adults. Notice in this case, in the interpretation, they did answer the question correctly, because the claim is the null hypothesis. So what are we attempting to do with our hypothesis test? We want to see if there's enough evidence to reject the null hypothesis, which happens to be the claim. So since we're not rejecting the null hypothesis, we're going to say there's not enough evidence to reject the claim. All right. Well, let's do some problems at the back of the book. If we go to page 392, all right, and we're going to look at these 13, 14, and 15. All right. Notice I picked these because it says hypothesis tested using a p-value. So we're going to show you, I'll show you how to do this. Space travel, let's do 13. A research center claims that 27% of US adults would travel into space on a commercial flight if they could afford it. So the claim is that 27%. This means is 27%. This is the null hypothesis, equal to 27%, as opposed to the alternative, which we would be not equal to. All right, so the wording here tells me equal to is the claim, and it's in the null hypothesis. In a random sample of 1,000 US adults, so n is equal to 1,000, 30% say they would travel into space on a commercial flight if they could afford it. So 0.30 is going to be our sample proportion. So up here, 0.27 is our hypothesized proportion. 0.30 is our sample proportion. At alpha is equal to 0.05, is there enough evidence to reject the researcher center's claim? Now remember, the researcher center's claim is the null hypothesis because it's equal to. This word that here, that 27% of US adults, that indicates equal to. All right, so let's go to solutions. Here's p hat, here's n, here's alpha. Here's our claim, the null hypothesis. Here's the alternative. If the null is equal to, the alternative must be the not equal to. All right. Now, the only thing I would correct here is I'm calculating n times p and n times 1 minus p. And p in this case is 0.27. So when I multiply 1,000 times 0.27, I get 270. When I multiply 1,000 times 1 minus 0.27 or 0.73, I get 730. I say they're both bigger than 10. I think your book says bigger than 5. It doesn't matter. They're so much bigger than both those numbers. We can say that the sampling distribution is approximately normal. So I'm going to change this because I want to be consistent with your book. I'll change these 10s into 5s so that there's no confusion here. But in most cases, any problems I give you for certain, n times p and n times 1 minus p will be definitely bigger than 5. And in this case, I said 10. But again, it doesn't matter. Step 3 is our test statistic. P hat minus p divided by the square root of p times 1 minus p divided by n. Now the numerator, remember that p hat is 0.30. Look above here. P hat, 0.30, that's our sample proportion. Our hypothesized proportion is 0.27. The hypothesis test. And the denominator inside here, we're going to use the hypothesized proportion, 0.27. times 1 minus p, which is 0.73, divided by n, which is 1,000. When I do this calculation, this is my test statistic, 2.1369. Now I'm rounding it to 4 decimal places. Now, since the alternative hypothesis, remember the alternative hypothesis tells us what type of test. If it has less than, it's a left tail test. If it has if it has less than symbol in it, it's a left tail test. A greater than symbol would be a right tail test, and a not equal to symbol is a two tail test. So in this case, it's a two tail test. So that means that whatever area that we calculate, in this case, because the z is positive, we're going to find the area to the right of it. Whatever area we find here, using normal CDF, it's going to be 1/2 the p-value because it's a two-tailed test. The other half of the p-values are on the left. So 1/2 the p-value is equal to probability that z is greater than 2.1369. We use normal CDF because it's a z. And because it's greater than, we put our lower limit as the 2.1369. That's our test statistic. Again, I'm going to use a big positive number for my upper limit, 1,000. And then the mean is 0, standard deviation is 1. So 1/2 the p-value, when I hit enter, it's going to be 0.0163. Remember, with the two-tailed test, I have to multiply this area here by 2, and I get 0.0326. All right. Since the p-value 0.0326, and I guess I forgot to put a number here. I think it's supposed to be 0.05. Yep, 0.05. So I must have erased it by accident. So there should be a 5 here, 0.05. Since 0.0326 is less than 0.05, we're going to reject the null. All right. So when the p-value is less than alpha, we reject the null. So since the null is the claim, we're going to say at the 5% level of significance, there is enough evidence to reject the claim that 27% of US adults would travel into space on a commercial flight if they could afford it. All right, so now let's go to number 14. Let's go and read it. Oops, there we go. Number 14, a research center claims that at most, 18% of US adults' online food purchases are for snacks. Now, when we use the term at most, what does that mean? That means less than or equal to. Remember, all the equal to symbols, equal to, less than or equal to, or greater than or equal to, are in the null hypothesis. So this is, again, a null hypothesis claim. And we're going to put less than or equal to 0.18. P is less than or equal to 0.18 is going to be our null hypothesis, which means that our alternative hypothesis will be the complement of it, which is P is greater than 0.18. Okay, we'll get to that in a second. Now, in a random sample of 1,995 US adults, it looks like 1995 is a year, but it's actually referring to the n, the sample size. So n is equal to 1995. 20% say their online purchases are for snacks. This 20% of 0.20 is our sample proportion. At alpha, or the level of significance equal to 1.10, which is 10%, is there enough evidence to support the center's claim? Now, once again, this is worded, I don't like the wording of this, because the claim in this case here is going to be the null hypothesis. So we're really going to be asking the question, is there enough evidence to reject the null hypothesis claim? So once again, not worded correctly. But again, in your test, I will make sure I word everything correctly. All right, so let's get to the solution. Again, n is 1995. Our sample proportion is 0.20, and our level of significance is 0.10. Step 1 is to state the null and alternative hypothesis. At most means less than or equal to, so that's going to be our null hypothesis. It says 18%, so we always convert the percentage to a decimal, which is 0.18. And that means our alternative is going to be greater than 0.18. All right. Step number 2, again, multiplying n times p and n times 1 minus p. We end up with these huge numbers. Again, I'll correct this, and I should be saying 5 here instead of 10, but it doesn't matter. These numbers are so much larger, it doesn't matter whether we state 5 or 10. Since they're much bigger than 5 or 10, the sampling distribution is approximately normal. Step 3 is our test statistic. Once again, the numerator is going to be p hat minus p right here. So p hat is 0.2, p is 0.18, and our denominator is the square root of, and remember we're using p, our hypothesized proportion inside the square root, so it's 0.18 times 1 minus p, which is 0.82, divided by the sample size, which is 1995. And when we calculate this, it's z is equal to 2.3252. We round it to 4 decimal places. Now, since the alternative hypothesis is greater than, remember the alternative hypothesis determines the test, and since it's greater than, it's a right-tail test. And our p-value is the probability that z is greater than the test statistic. It's this right-tail area to the right of the test statistic. And if we use normal CDF and use the lower limit as the test statistic because it's greater than, and the upper limit is 1,000, you get our p-value is 0.01. Step 5 says since the p-value is 0.01 and that's less than alpha's 0.10, don't confuse these two. This 0.01 is 10 times smaller than the alpha. We're going to reject the null hypothesis. This is a clear case of rejecting the null. So we're going to say, now remember in this case here, the claim is the null hypothesis. So definitely rejecting that claim. So at the 10% level, significance level, there is enough evidence to reject the claim that at most 18% of US adults online food purchases are for snacks. Go back to the book. That's exactly the way they're going to write it up. All right, let's look at number 15, last one. A humane society claims that less than 67% of US households own a pet. So this is a clear case of less than. This must be the alternative hypothesis, right? Because less than is always in the alternative hypothesis. So it's a clear case that the claim is in the alternative hypothesis in this particular case. In a random sample of 600 US households, 600 being n, our sample size, 390 say they own a pet. All right, here's another case where they don't give you the proportion, but you have to calculate it. You're going to have to say 390 is our number of successes here, the number of people who say they own a pet out of the 600. So 390 divided by 600 is going to be our sample proportion. At alpha is equal to 0.10, is there enough evidence to support the society's claim? And this is actually worded correctly because the claim is in the alternative hypothesis. So let's look at the solution. All right, in the solution, sample size 600. The number of successes X is 390. The number of people in the survey 600. Alpha is 0.10. Step 1, here's our null and alternative hypothesis. So they stated in the problem that the claim says less than, so its p is less than 0.67, which means that the null hypothesis is the complement of that, which is greater than or equal to 0.67. Once again, n times 1 minus p is very large numbers. We take 600 and multiply it by 0.67 and also by 0.33. We end up with these numbers much bigger than 5 or 10. So clearly the sampling distribution is approximately normal. Now, step 3, we're going to do our test statistic. But first we have to calculate our sample proportion. Remember, X is 390 and N is 600. So our sample proportion is X divided by N. And when we divide these two numbers, we get 0.65 as our sample proportion. So that's what we plug in for p hat in our test statistic formula, 0.65. Our 0.67, which comes up from our hypothesis test is the hypothesized value that we put in for P. So the numerator is 0.65 minus 0.67. The denominator is, again, square root of, and again, we use our hypothesized proportion P inside the square root. It's 0.67 times 0.33 divided by 600, which is the sample size. When we calculate this, we get negative 1.0419. So that's our test statistic. All right. Now, since the alternative hypothesis is less than, this is a left-tail test. So you can see I'm drawing the standard normal curve, the z-curve, and I'm putting the test statistic to the left. It is negative, so it's to the left here. And the area to the left happens to be the p-value. It's a left-tail test. So the p-value is the probability that z is less than the test statistic of negative 1.0419. Again, using normal CDF. Because it's less than, we're going to put in the test statistic is the lower n. Oops. And I think I made a mistake here. I did this before last time. I don't know why I do this. So this is incorrect. I will have to change this in the, so there's a couple different mistakes I've made on this today. But because it's a left tail test, this should be negative 1,000 on the lower end, because it's a left tail. And the upper end should be negative 1.0419. I apologize for that. So this p-value could be incorrect, actually. So let's go ahead and do this problem correctly. Let's go to our calculator. All right, so I'm actually going to put in, I'm going to do this problem with my calculator now. And I'm just going to put in what I need to put in. And all right, so let's actually do this problem. This p-value could be incorrect. This whole solution here could be incorrect. I'm going to have to probably correct it. All right, so I apologize for that, but let's go ahead and show you directly what we should be doing. So once again, the sample proportion is going to be 1161 divided by 2202. Excuse me, that's wrong. And I am having a little bit of a brain freeze here, and I apologize. So I'm looking at the previous problem. It's actually, the numerator should be 390. There we go. And it's divided by 600, or sample size is 600. So this is going to be our sample proportion. All right. Now, since it's 0.65, one thing I could do is save it. I'm going to save it. So I'm going to store it. So I'm going to store it in A once again. Now I'm going to do my formula for my test statistic. So it's p hat, which is in A, minus the hypothesized proportion of 0.67, divided by the square roots. And remember, inside the square root for the standard error, I'm going to use 0.67, the hypothesized proportion. So it's 0.67 times. Now, what if I I was lazy and I didn't want to calculate 1 minus p in my head? I could simply open up a set of parentheses and say 1 minus 0.67, close parentheses, and then divide this by the sample size of 600, and enter. And there's my test statistic. I'm going to store that in T. All right, so my test statistic's now in T. Now this is a left tail test, so I'm going to do second VARS. And I'm going to scroll down to normal CDF. And once again, I'm going to use negative. It's a left tail test. So I'm going to use negative 1,000 here. I'll put T in the upper. That's what we do. We put our test statistic in the upper for a left tail test. Oops. And once again, made an error here. So I'm going to put T in here. All right. leave everything the same. It's a standard normal. Hit enter. Oh, it looks like it did do the p-value correctly. All right, so let's go back and see my solution. Yeah, I did this correctly, and I must have accidentally wrote down the normal CDF incorrectly here. I'll change that. Remember, it should show negative 1,000, comma, and then it should be negative 1.0419 in the second number. That's what should be there. All right, this is a left tail test. So I will correct this here, but the p-value, I must have done it correctly in the calculator because this is the correct p-value, 0.1487, rounded to the 4 decimal places. All right, so now the alpha is 0.10. It's a 10% test, a 10% level of significance. The p-value of 0.1487 is larger than alpha's 0.10, so the conclusion is do not reject the null hypothesis. So because this claim is the alternative hypothesis, when we do not reject the null, that means if we're not rejecting the null, that means we're not supporting the claim. So that's why I'm saying at the 10% level, significance level, there is not enough evidence to support the claim that less than 67% of U.S. households own a pet. All right, so these little corrections I will do before I post this today with the video. Apologize for those errors, but again, I'm a little sleepy today, so that's probably the reason for it. Anyway, that is it. That is hypothesis testing for proportions. And so we've now completed Chapter 7. Section 7.5, stop sharing here. Section 7.5, which is hypothesis tests for standard deviations and variances. We're not covering that in this course. So just like we didn't cover 6.4, which was confidence intervals for standard deviations and variances, we're not going to be covering hypothesis tests for those either. So this is it. So I will post this, obviously, if you see this, you know the video is posted, but I will also post homework today, 7.4 homework. Should also have the corrected section 7.4 problems that I went over today. All those couple different errors I will correct so that they are correct, they're posted correctly. And that is it for today. So anyway, what do we do for the rest of the course? Well, we've completed all the new material. So what I'm going to do on Monday is to post on Monday a sample test 3. So Monday, which is May the 4th, I will post that sample test. You will work on it during the week, and on Friday, I will post the solutions on Friday. Okay, so and then the following week, on Tuesday, which would be May 12th, will be test number 3. Now, it's very important that you take test number 3 on May 12th, unless there's an emergency. Please don't come and tell me you forgot about it or anything like that. I'm going to send you several email reminders about it. That is the final day of the course, is May 12th. So again, unless there's an emergency, maybe you have some equipment issues, you have a coronavirus issue with yourself. I hope not. I hope that you and your family are healthy. I certainly don't want anybody to be walking around sick with this. So, you know, that's the issue. Certainly, I will work with you. But for everybody else, there shouldn't be any excuses. You should be able to take the test on May 12th. Again, I'll open it up at 6 a.m. on May 12th, and it'll close at 11:59 a.m. Make sure you test everything out earlier in the day. Make sure your computer's working, to make sure internet's working, in case you run into an issue with that, and then maybe you can borrow somebody else's computer or go somewhere else to take the test if you can. But again, that's it. I will have, again, Q&As this week and next week. But that's it for the course. So this is the very last video, and I hope these videos were helpful to you. I know this was a difficult situation to go from in-class instruction to online instruction, but I did the best that I could to give you the information that you needed, step-by-step instructions on how to use your calculator, and hopefully you will all be very successful in the course. All right, so that's it, and hopefully you'll also take advantage of those Q&As. Again, there will be one today and one next Thursday, and that will be it for the Q&As also. And remember, all the homework is due on May 8th. I will not accept any homework past Friday, May 8th. So make sure that you complete all the homework on time. All right, I'm giving you so much time, lead time on this. There should be no reason why you should be late in completing the homework. All right, that's it. Again, good luck to all of you. And again, I will be sending you email reminders about the sample tasks when it's posted in Canvas. And I'll post solutions and give you plenty of notification about our test number 3. Remember, there's no final exam this year, just 3 tests. All right, that's it. So have a good day.